Good day, students.
Good day, sir.
The topic for today is elastic properties of solid. The subtopic is Hooke's law. But before we go into defining what Hooke's law is all about, I would like to define to you elasticity. Elasticity is defined as the ability of a material to return to its original shape and sizes after being deformed. Having known this, I would like to ask you a question. I want somebody to mention 2 examples of material that is elastic in nature.
Rubber band.
Rubber ring. When you stretch a rubber ring or compress it, what happens? It returns to its original position. Good. Another example of elasticity. Lois.
An elastic spring.
Elastic spring. Thank you very much. All these are examples of elasticity or material that are elastic in nature. Now, having done this, let's go back to Hooke's law. The idea behind Hooke's law is this. This is what we call elastic spring. Somebody made mention of this when I give an example of elasticity. This elastic spring. Okay. When a load is added to this elastic spring, there's every tendency that the elastic spring will increase in length. True or false? True. Good. And when the load is removed from it, what happens? It returns to its original what? Position. That is it. Let me define Hooke's law. Hooke's law states that provided elastic limit is not exceeded, the extension of the material E is directly proportional to the applied force F. And what do we mean by that? It means F is proportional to E, while F is equal to what? KE. K is equal to what? F over E. Let me define these terms. F stands for force. E stands for what? Proportionality constant. While E stands for extension. Thank you very much. Good. Before we go into further calculation on Hooke's law, I would like to explain to you the relationship between force and extension. This is what we call elastic spring. This is what? Return stand. And this is what? 100 meter. These are a set of masses, weight, okay, of different sizes. They are all in grams. Good. First, you try as much as possible to fix your elastic spring on this return stand. And when that is done, different masses to be given to you of different sizes depend on what the examiner is asking you to do. If they say 50 grams, you fix 50 grams. If they say 100 grams, you fix it. And when that is done, you have to measure the original length. This is what we call the original length. The original length of the spring have to be mentioned. You measure this, and if you are to measure this, this one is given to be 9.5 centimeter length. This is the length of it. The length of this spring is what? 9.5 centimeter. Good. This will take us to table of value. Here you have the masses in grams. This is the original length. And after the original length comes the reading of the spring. Then after that we have the extension. All these are in centimeter except the mass. Let's assume that these are the masses given to you. This is 50 grams, 100 grams, 150 grams, as the case may be. The original length is fixed. As you can see, the original length is fixed, 9.5 centimeter. Let me teach you a modern way of writing this. You don't write the centimeter by the side. The centimeter is always on top. If you have the unit on top, no need of putting it by the side anymore. Can you see the one we did here? The grams. The gram is already here, so no need of putting grams, writing 50 grams, 100 grams, 150 grams, as you can see. All these are in centimeters. Now, let's take the reading. That is, when 50 grams is added to the spring, what's going to be the length? This is 100 grams. This is 50 gram mass. We are suspending this. We are going to add this to the spring. Now there is a little ship. I hope you can see it. All right. So we'll measure this. Ideally, we're supposed to take it twice. Sorry, this is 10.5 centimeter. 10.5 centimeter. No need of putting centimeter because centimeter is already here. Please don't make that mistake. 9.5 centimeter, this is how we write it. You don't just write 9.5. You have to put 0 by the side. 9.5 centimeter. Now, how do you get the extension? For you to get the extension, you have to subtract the reading from what? From the original length. That is 10.5 minus 9.5. What's the answer? 1.0 centimeter. Good. 1.0 centimeter. Then, maybe this one we are asked to add what? How many grams? 100 grams. So you have to look for another 50 grams to add to this. Good. Can you see it? Then when that is done, you measure this. Good. This is 12 centimeter. 12 centimeter. Remember, this one is fixed. The original length is fixed. This is what? 12.00 centimeter. And how do we get the extension from this? 12.00 minus what? 9. So what's the answer? 2.5. If you continue with this, till when we get to 200, let's say this is 200 grams, right? Something happened. You experience that there is a shift from the spring. So let's try that and see. If we continue to add this, time will come whereby when I remove the mass, or if the mass is being removed from the spring will no longer return to its original position. What is the tense used in describing that scenario?
Elastic limit.
Thank you very much. By the time the mass is removed, it no longer returns to its original position. That's the elastic limit. At that point, which the spring loses its elastic limit, at that point we can say it is what? Described as yield point. Thank you very much. So based on this, you continue fixing all this until when you arrive at the final bus stop, where the teacher says you should stop. Then you plot your graph. And when plotting your graph, this is the nature of your graph. The nature of the graph is going to be a straight line graph. I told you right from the beginning that we are trying to establish the relationship between what? Extension and load. This is your extension. This is your what? Your load. Now you have to plot in your graph. First, you choose your scale. You choose the title. The title is, maybe it depends on what the teacher asks you to do. Plot the graph of extension against load. Or plot a graph of load against extension. Then you plot. But what we are to know at this point is that when you draw your graph, it's going to be a straight line graph. This is how your graph will look like. Let's move on to the other section. The formula for calculating slope. Change in the y, all over change in the x. That is y2 minus y1 all over x2 minus what? x1. Good. You know the value for x1. This is y-axis. This is what? S-axis. This point is your what? This is your final x. That is x2. Then whatever you have here is your what? Your s1. Then this point here is your what? This is your y2 minus your y1. Whatever value you have, you substitute with this, and that is the end. Good. Let's move on to the calculation aspect of it. We want to solve problem with this. And after that, I'll be asking you a question. All right. Problem number 1 that we are asked to solve using Hooke's law. Now, I've given you the formula for Hooke's law. And I want you to apply that formula in solving this problem. I also want to give us the value for 150 grams. In 150 grams, we have 10, that is 100 grams solid, right? So our own is to add another 50 grams mass to make it 150. So let's add that and see. Okay. You can see that there is a little shift from the former length of the spring. So we'll measure this. Is 14.5. 14.5. I told you this one is fixed. The original length is fixed. 14.5 centimeter. What's the value for the extension? The first one, 1.0. The second one is what? 2.5. The third one is what? 5.0. Let's go to the final stage. That is 200, right? This is 100 grams. This is another 100 grams. I'm going to add this to this. All right. Please take note of this. We are not measuring the length of the hook. From where the hook ends, where the spring attached to the hook that we measure. This is 16.5 centimeter. 16.5 centimeter. What is the difference between 16.5? That is, subtract 16.5 from 9.5. What do you have? 7.0. All right. Let's make 250. When we're adding 250 grams to this, our own is just to add 50 gram mass to the one we already have. And let's see what will be the shift. This is 19.5 centimeter. Please, when you are done, make sure you remove this. If not, it will affect the spring. What do I say is the value? 19.5. So subtract 19.5 from 9.5. What do you have? 10.0. Good. We are going to plot the graph of force against extension. Some of you will be confused. Where is the force? I told you either force or mass. They are all the same, right? The weight, that is the object here, added to this before taking the measurement. This is our force. Apply. So we are going to plot graph. And then from here to here is what? 200. From here is what? 300, 400, 500. Good. Now, remember, I said the title is what? A graph of what? Of extension against load. Scale. We say the scale on y-axis or extension axis is what? 2 centimeter to represent what? On extension axis. Let's assume that from here to here is 1. That is 1 box. From here to here is another 2 boxes. Okay, let's say this is 2 boxes. Here, here. 1, 2, 3, 4, 5. Can you see what I'm doing? That is in a assume that this is graph. You have a line like this. Means from here to here is 1 centimeter. Then from here to here is another centimeter. This is also 2 centimeters to represent what? 100 units. On what? On load as okay. 2 centimeters to represent what? 100 units on what? On load axis. Good. So, I want you to be very careful now. I want to see how we can plot this. This is extension, and this is load. M. Okay. And just put M in place of load. When it is 2, this is 1, right? So we assume that there's 1 in between 0 and 2 is 1. Is that not? Yes, okay. So let's see 50. 50 is half of 100. Are you getting what I'm doing? Yes. Okay, the half of 100 is 50. That is from here is 50. That is 1 centimeter here is 50. So 1 is going to be from here. From 0 to 2 is 1. So in between this and this, you have 1. You have to start it this way. Now let's move on to the second one. When it is 100, when load is 100, okay, when load is 100, extension is what? 2.5. Okay. This is 2. In between 4 and 2 is what? 3, right? So 2.5 is going to fall within this level because the middle of this is 3, right? So 2.5 is going to be somewhere here. So when we have 2.5, we are having what? 100. So you have to mark this. This is 100, column of 100. So you're having something like this. So you put asterisk. Please take note of the first one. We have something like this. So when it is 150, 150 is between 100 and 200. So half of this will give us 150. So 150, what do we have? We have what? 5. So 5 is going to be here. The difference between 6 and 4, we have 5 in between, is that not? So half of this is going to give us what we want. The next one is what? 200. 200 will give us what? 7. Which means 200. We have 7 between 6 and 250 will give us what? 250 is between 200 and 300. 10. All right. So please try as much as possible to wipe off this. I'm just putting the dots so that you know the margin, to know where it falls in. This is what I was trying to say. If you take a look at this, you discover that this is a straight line graph. It's not more than all the line must fall within the middle line. There's something we call line of best fit. At most, let it be 3 lines. By the time you rule it from the beginning, that is from 0 axis. It's not must, and don't force the point to be in a straight line. All the points must be in a straight line when you rule from 0 axis. So take note of this. As you can see, these few lines fall within, the points here fall within the straight line, but the rest is on the outside. This one is outside the straight line, but this one is very close to the straight line. But those ones are within, those points are within the straight line, or fall within the straight line. So you rule. Now if you're asked to find your slope, you apply, you can choose your slope from any point. From any point. If you like, you can choose from here to here. This is your slope. Then how do you get the slope? Mind you, from here is what? 7. Is that what this is 7. 7 what? 7 centimeter. So this is 7. This is going to be your what? Your y2. But before we go that, I would like to write the formula for slope. Slope is given as what?
y2 minus y1 over x2 minus x1.
y2 minus y1 all over x2 minus x1. y2 equals to what?
7.
y1 equals to what?
2.
x2 is equals to what?
250.
Then x1 equals to
100.
So 7 minus 2, what do you have? 250 minus this. So 5 divided by 150, what do you have?
0.033.
What? 0.033. This is the slope, the value for the slope. So with this, we've arrived at the answer. That is the slope. So let's go back to some mathematical expression on Hooke's law. So problem number 1. A force of 0.8 newton stretches an elastic spring by 2 centimeters. Find the elastic constant of the spring. First, you apply the formula for Hooke's law. Elvis, what's the formula for Hooke's law?
The formula for Hooke's law is given as F is directly proportional to E. That is F equals to KE.
F equals to what? KE. Good. But from here, what are we asked to calculate?
Let's calculate K, which is proportionality constant.
Proportionality constant K. So you make K the subject of the formula. So your K is going to be K equals to what? F over E. What's the value of F from the question? 0.8. Good. 0.8. What's the value of extension? 0.02. Please take note of this. Here, extension is in centimeter. But what is the unit of extension? Meter. So you have to convert this centimeter to meter. That is 2 divided by what? 100 will give us what? 0.02. So 0.8 divided by 0.02. What do you have? 40. Good. 40. Now let me ask. This is proportionality constant. What is the formula? Sorry, what is the unit of proportionality constant K?
The unit of K is Newton per meter.
Thank you very much. Newton per meter. Why is it Newton per meter? The unit of force is what? Newton. The unit of extension is what? Meter. So that is it. Question number 2. The question says, a spring of natural length 3 meters is extended by 0.01 meter by a force of 4 Newton. What will be its length when the applied force is 12 Newton? I want someone to come and solve this. Who can do that for us?
Hooke's law states that F is proportional to extension. That's force proportional to extension. That's force equals to KE. So we're bringing out our data. Then a spring of natural length. So you are not done. You not say your applied force is equals to 3 meter. Say 3 plus
Extension.
extension is 0.03. Now say 0.03. Figure
3.03 meter.
Let me have it. Is she right?
Yes.
Good. Put your hands together for her. Thank you very much. As you can see, that is the answer to the problem. We're given two forces, force 1, force 2. Under this condition, then we are given two extensions. One extension is given, the other extension is unknown. So you are asked to find the second extension. So you have to apply the Hooke's law. First, you get your extension, proportionality constant. Get your proportionality constant, which is K, before you can now substitute and get it right. Now, before you can solve this, you have to what? Get your data first. Your F1, F2 must be taken note of. Then your E1, E2. Then your K also will also be taken note of. Then after that, you can go straight and solve. Thank you very much, Lois. You tried. With this, we've come to the end of today's class. See you in our next class.
Thank you.